microphone. So just testing that out. Can everybody hear okay? Excellent. Good. I see thumbs up. Hello everyone and welcome. My name is Naomi Balabujo and I'm the CEO of the Deep River Library. And I'm here this evening with my colleague Alex behind all of that technology there. Alex is our newest library assistant in the role of digital services and he joined us this September. We're thrilled to have him here and he's recording this evening's presentation and we'll post it shortly on our YouTube channel, so please keep your eye out. Eye out. I'd like to start by recognizing that we gather on the traditional and unceded territory of the Algonquin Anishinaabe people. We honor the rich history of the Algonquin people in this area, including those who built their homes and lived here until the 1940s when the town was established, and who stayed here and have roots as our friends and neighbors. At the library, we work to research and share this history. There's a pamphlet by the door if you're interested. We aim to include and celebrate Indigenous knowledge and stories in our collections and our services, and we strive to provide opportunities to learn together on this journey towards truth and reconciliation. A few housekeeping items before I pass the microphone over to our wonderful co-host Mike Milgram. As you probably all know, the washrooms are just on the other side of that wall. Emergency exit is out that door and to the left. You might have noticed that the elevator is well under construction, but in case of emergency, you should still not use the elevator. So please, if you need assistance leaving the building, meet in the bottom of the stairwell. I hope that you will stay for coffee, cookies, and conversation at the end of what promises to be a very interesting presentation. And I will now pass the mic over to Mike.
You're going to have to think of a different line next time. So my job here tonight is to introduce the speaker and to introduce the seminar series. And I will try and keep it as short as I can because I know you are here to hear the speaker, not me. But again, my job is to let you know what we've got planned. To remind you, last talk we had was Dave Beatty talked all about drones. Tonight, Phil Deacon is going to talk about his visit to the Atacama Desert and telescopes. Next talk will be by Mark Ungren. Now, most of these speakers are intended to be people who live in Deep River or in the area anyway, and give them a chance to, a platform to tell us what they're doing. Mark grew up here. He lives in Calgary, actually, but he's resident in Deep River for a year, so we grabbed him while he was here. He is a professor in the Department of Veterinary Medicine at the University of Calgary and is deeply involved in public policy, in particular the use of masks, the different masks that people use when there's pandemics. In January, Brendan Quine, who is the Chief Operating Officer, I guess that's the title, of Thoth Industries, who runs the Algonquin Park Radio Telescope and is also the owner of what used to be the dairy, is going to tell us what he is doing, which I'm very interested to find out. After that, Anne Serdula, who I think a lot of people know, will tell us about lost villages of the St. Lawrence Valley. Apparently, Anne grew up in a town which is now underwater. And she will talk about all the towns which were destroyed in the building of the St. Lawrence Seaway. John MacDonald has spent 50 years building timber frame dwellings, and he is going to talk about his career doing that. I believe, if I know John, he'll probably bring along his guitar. And Richard Wilson will talk about diseases of trees. Now, anybody who's got a good memory might notice that we've made a change in Richard's talk. It's now April the 10th. So if you went home and when you first saw this seminar and saw a date for him, please change your calendar if you made a note. For those of you who are new, the purpose of this seminar series is to give people the opportunity to tell us what they've been doing. And there are simple rules that I think most of you know. I'll save you that again tonight. I can also tell you that next year I have a full slate of speakers, so if you're thinking about giving a talk, you've got a 2-year wait to plan. But if you want to get on the waiting list, please speak to me sooner rather than later. So that's, and one more thing, that we do not have an entrance fee, but we do have a jar at the exit, which will allow people to make known what they thought of the talk they have just heard. It's a voluntary exit fee, and what we collect is going to the food bank. So I now get to introduce our speaker, Phil Deacon. Phil is a resident of Deep River. Well, he's not. He's a resident of Laurentian Hills, but that makes him almost honorary resident of Deep River. He came here, I'm not sure how many years ago, from CMHC in Ottawa. He has been very active in quite a few groups around town. He has a background in a very great interest in telescopes. He owns one of his own. And when he saw an ad for a tour of the telescopes of Chile, he jumped aboard. And tonight he's going to tell us about it. Phil? Mention questions at the end.
Hi. So, good evening, everyone, and thanks for coming out on such a miserable evening. I wondered how many would come. If it had been me, I probably wouldn't have bothered, but... Yeah, so I've been fascinated by all things space, basically, since I was about 9 or 10 years old. And I'm going to talk a little bit about my introduction to it. I'm going to introduce you to the person who got me interested, and we'll go and introduce him right now. So, yes, it was Dan Durr. He was a rocket ship pilot in the solar system, and he saved the Earth, multiple times from the evil Treens. That's the guy, the green guy at the back. He lived on Venus. He was the ruler, and he had every week had a new scheme to dominate the Earth and invade it. And it was up to Dan Durr to fly to wherever it was, Saturn or Neptune or Jupiter, and foil the evil Mekon. Every week on Fridays. So he would fly around the solar system. It didn't really tell you exactly how long it took him to do this, but he was always back for next Friday. So it couldn't have been that long. Anyway, so since then, this was about 1956 or 57, and it was actually just at the beginning of space exploration. About that time, Sputnik went up, and then there was Telstar and other satellites, and then the Russians put Yuri Gagarin up into space, and then there was Alan Shepard on the American side, and then it was like a tussle between Russia and the US forever, getting stuff into space. It was fascinating stuff, and along the way they kept learning things. So just at that time it was just the planets, the solar system. Even I wasn't really aware of stars, why they were different or anything. But 70 years later we find that we visited all of them, either not really personally, we only ever got to the moon, but it was through robotics and all sorts of weird and wonderful devices. We've sort of visited almost everywhere in the solar system, and we've learned about it a lot. So there have been flybys, probes, orbiters, landers, rovers, and on Mars, even a helicopter. So it's wonderful science. Machines are obviously the way to go. It's a lot easier to get the machines up there than it is to get a person. But stars are different anyway. It's a different field completely because they are just so far away that we're not really ever going to get there. At least I don't think so. And so all you can do on stars is observe them. That's all we can do. So where are the stars? Well, all the stars that you can see with the naked eye are in our own galaxy, the Milky Way. And the Milky Way is a spiral galaxy. If Dan Dare had a really, really fast rocket ship, he could go up, driving towards the galactic North Pole and take a picture looking down, and it would look something like that. You can see that we're not really in the middle of it. The sun is down here. We're in one of the arms that trail around. We're about halfway out. The diameter of the spiral of the Milky Way is 100,000 light years. So that is light from one side of it to the other side. It would take 100,000 years before the person could see it and go, hi. So it's a big galaxy. It's not the biggest galaxy there is, but it's a pretty good sized one. And we're about halfway out, 26,000 light years from the center of the bulge. All of those spirals have names. There's a whole lot of science behind why they form, but I'm not going to get into that now, mainly because I don't understand it. So anyway, so the Milky Way, if you looked at it on edge, it would look a bit like this. So you can see that the spirals are actually quite thin when you look at them on edge. They're only about 10 light years thick at the edges, and the bulge is the middle, it's about 100 light years. And most of the stars, there's about 400 billion stars in the Milky Way. Half of them are in that central bulge in the middle. The rest of them are spread out in the arms. And this is what they look like from the northern hemisphere and the southern. So the one on the left is Manitoba. The one on the right was taken in the Atacama. There's a lot more stars in the right-hand one, and that's the main reason I went to Chile. So why would that be? We never get to see all the stars. Even though everything is rotating, you'd think that sometime we'd get a good view of them, but we don't. And the reason for that is because the solar system is tilted. It's biased towards the southern hemisphere, which I think is unfair, but that's the way it is. So this diagram shows the central bulge is there. The horizontal line is the galactic plane. That's the flat plane that the spiral revolves in. So the sun follows along that galactic plane, but the solar system, and that's the orbit of Earth around it for illustrative purposes, it's tilted. It's not flat like in the spiral galaxy. It's tilted up by about 60 degrees. Worse than that, it's tilted up also to face away, at least for the northern hemisphere, to face away. So that's my model of the solar system is here. So instead of, ideally, we'd go around flat along the galactic plane, and north and south we'd get equal views of the central bulge different times of the year. When they're facing away from the sun, it'd have to be towards the ring. Half the year it would be facing out into the space, and we just see what we see in the northern hemisphere. So this is not going around like that. It's tilted by 60 degrees, and then worse, it's tilted by about another 60 degrees that way. So we're on this side of it with my little finger, and that is going to always face away from the central bulge as it goes round. But it won't always be like that. It'll be because the whole Milky Way is rotating, and through gyroscopic inertia, we will always be facing that way. So we'll always be like this, going round. So eventually, set your date times here, we will see what they see in the southern hemisphere. It'll only be 125 million years in the future. So I don't think my calendar works that far ahead. The best that we can see, the closest we can see to the central bulge is midsummer, the solstice, June 21st or something like that. And if you look right down on a very, very clear night on the horizon, if you face due south, you'll see in the constellation Sagittarius and then Scorpio on the just to the right of it. That is the center point of the galaxy. That is Sagittarius A star, which is the name given to the black hole in the middle of our Milky Way. It's a massive black hole. It's quite a big one. And I'll mention that in a bit later on. It'd be very difficult to see because it's right on the horizon and it's still summer, so there's still a lot of residual light in the air. The contrast is terrible, but on a really, really clear night you might see something. So we can't get to them, we can observe them. So Chile, as it turns out, is a wonderful place to go and do this. So astronomers have been looking at stars forever. They have star catalogues going back to Ptolemy, 2,300 years ago or whenever it was. And people have been trying to record stars all the time since then. Galileo made a big advance with the telescope. Suddenly, stars were brought right close to his eyes. He could see a lot more. He added a whole lot of stars there that people couldn't actually see without a telescope, but he did a lot. And since then, Newton with a reflector telescope, Herschel made super advances in telescope design, and it was really quite an explosion of design work in the 1600s onwards. So the modern telescopes are a huge, not technological marvel. There's two types, basically. Telescopes fall into two types. One is observing distant objects, trying to bring them as close as possible, trying to resolve one. Like if you see two things together too far away, it just looks like one blob. But a good telescope will bring it up close and you can see that it's actually two. So that's very good for looking at binary stars, of which there are many. And then the other one is observing changes in the sky. Things that go, stars explode, supernovae, basically asteroids come close to Earth. That's a good one, very current, that one. And so observing changes or transient phenomena is the second category, general category of telescopes. So while we were in Chile, somebody brought along a telescope, and it's just a carry-on thing. I got one myself quite recently. I haven't used it yet. only got it 10 days ago. And these are just a selection of photographs that he took. So the first one is in the constellation, the Toucan constellation. Toucan I-47 is a globular cluster. This is a group of stars that are condensed out of a huge mass of hydrogen and kept together. It's like a real glory. The more you look at it in a big telescope, it's just like star after star after star. It's quite astonishing. Other things you see are nebulas. These are clouds of gas and just material, often from the remains from a supernova or something. So it's gas been exploded and spreading out through space. They always look very nice in reflected light, and the other stars of course, reflect onto them, and that's what gives them illumination. So this is in the Carina Nebula, and is quite a big nebula. It has a lot of little things to look at it inside it, and one of the ones is the Tarantula Nebula on the right. So you can't see those from here, but you have to go to Chile. It takes about 11 and a half hours on a plane. So when I was in the Atacama, we visited this town called San Pedro de Atacama. It's an oasis town in the middle of the desert. It's fed by a few rivers that flowing down from the Andes Mountains. The river flows through the town and for a few miles afterwards, and then it peters out in salt lagoons, basically. And it's a very beautiful place. Astrotourism is a big industry now in Chile. You'll see references to it all the time. So there are many places in San Pedro and in and around San Pedro that cater to tourists that want to go and look at stars. And so this one that we went to look at was in Io Crux, and it's basically where one of the rivers comes through and sort of ends. It used to be a shepherd's hut with various pens, and they took it over and cleaned it all up, and they don't do any sheep farming anymore there, and converted it. So the one on the left is a reflecting pool. So the sheep needed water, so they collected the water that there was, and built a really nice spot to there. They take people's photographs next to it. It's lovely. You get stories there about how, because the density of stars is so high, that using stars to try and read what time of year it is for planting crops and things like that is very difficult. There's so many stars. So what they used to do was look at the reflection in a pool. That sort of takes out a lot of stars, and only the very bright ones come up, and they can use that to determine when is the best time to plant corn or whatever it might be. On the right is another open area that used to be used for a sheep pen. So they cleaned that up, and when they have a group coming in, they get inflatable air mattresses, and they put them down on the ground, and they say, have a pair of binoculars, or just go and lie down and look up at that sky, and you'll be amazed at how much, when you spend time looking up there and doing nothing else, you see more and more and more. And then using binoculars, it's incredible. It's absolutely incredible. So that's what I did. I think I was there for 25 minutes, and just looking at the stars. So, why is Chile, the Atacama Desert especially, such a wonderful place? Well, it's got everything's going for it. One is it's at the right latitude. It's in the just about 25 to 30 degrees. That's the high pressure zone, and all around the world, and around that latitude, you get high pressure. There's a very cold current comes up a trench all along the Chile coast, and that really discourages any form of cyclone development. It's too cold, so no storms along the sea. Also, very good seafood, wonderful seafood. It's one of the biggest fishing areas in the world. So another thing it's got is the fact that it's down at the latitudes where trade winds blow, coming in from the east, and they hit the Andes, and they go up, they cool off, get rid of all that moisture, and then they go over the top and come down, and so the adiabatic, and the winds warm up. So you have this warm wind. It's like a Chinook, basically. You have this warm wind blowing across, and it's a dry wind, and it means that everything dries out. It's dusty, on the desert side of things. So the yellow area is the actual altiplano, which is basically very high ground, and which is where a couple of telescopes are there. A little bit further down, the orangey area is much more rugged terrain. It's mountainous, and that it seems like every mountain top that you can see seems to have an observatory on top of it. So there are in fact a huge amount of telescopes in Chile. So there are 63 that I sort of Googled and found in lists. Some of these, I must admit, they are old and probably disused, and a few of them there are in the process of being built now. And but there they are, and this is the telescopes basically of about 1.2 meters or bigger. Some of them are up in the 8 meters, which we'll be looking at soon. Many of them are very specialized, just built there for one particular purpose. So, and run by universities in Europe. They run them all remotely, and anyway, so it's absolutely quite the center of astronomy. So what type of telescopes are there? Well, there's two types. One is distant object ones. The purpose of this is to gather light, to make dim object brighter, and to increase resolving power. So basically it boils down, the larger the aperture, which is often the diameter of the telescope lens or the mirror, the more light it can collect from faint, distant objects. And you can see the dimmer stars, the galaxies, other celestial bodies that normally are invisible to the naked eye. The other one is, of course, to resolve like small objects. Are you looking at two objects, or is it one object there? So that, again, the large aperture gives more resolution to that, and so you can distinguish between two objects like a binary star systems, which are very common. In essence, the bigger the better for this type of telescope. And every new telescope that gets announced is bigger than the one before. It seems that way. The other type of telescope is just observing changes, essentially. So mapping, cataloging, recording all that information. It provides a data set, a foundation for other telescopes to use when they want to do research on a particular star. And of course the big one now is time domain, taking photographs of the same area of sky again and again and again, and then comparing them and seeing what's moved. So this is big now in asteroid detection, and we'll talk about that a bit later too. But the essence of that is the faster the telescope can do it, the better. So yeah, when we receive light, it's on our retinas, or nowadays on telescopes, it's on sensors, and the visible light is really that. I mean, that's all that we can see, but that's not to say that that's the only radiation that's going out there. The stars put out radiation, a lot much more, but not all of it gets through our atmosphere. So this is the electromagnetic spectrum. Light is electromagnetic, and it's a tiny fraction of the whole thing. So over on the right, you have nasty gamma waves here. These are things that we don't want to be looking at. They're very dangerous. This is ionizing radiation. It can affect molecules, including your DNA. So we don't want that too much. Moving to the left, we're getting into X-rays. Everybody's familiar with X-rays. further on, we're getting into the ultraviolet area, and then you get to visible light. So the near ultraviolet to the visible light is what you put sunscreen on for, because that can burn the skin. But essentially after that, it's harmless. So as you go in, you go past the visible light spectrum from violet all the way through red, you get into infrared. And that's where a lot of telescopes do their observing, because for infrared, the infrared can pass through nebulas, which is like dust clouds in the universe. Just looking at it visibly, you would not be able to see a star. It'd be obscured by a nebula. But the infrared, it'll pass through that. And then you keep going to the left. We're getting into microwaves, then into radio waves. And you can see that some areas are really opaque. Doesn't come up very well on this slide, but this is pretty much opaque up to the near ultraviolet. And then this is also opaque over here. You get little windows of transparency, and then over in radio waves it's completely transparent. So if you're going to be doing any observing, you have to take advantage of those windows where the atmosphere doesn't get in the way. So let's take a look at a telescope for distant objects. So this was the first visit that we did, was to the Very Large Telescope. It is at Paranal. It's on the coastal mountains of Chile. Now, I know you're going to say, did I say the Very Large Telescope? Because there seem to be more than that. And there are four telescopes. Those are the big units. Actually, I lie. There are 8 telescopes there. As these little guys, there and there and there. There are 4 of those as well. And they can move around on rails to different positions on the platform. Oh, going back, there we go. So this is the platform of the Very Large Telescope. And those 8 telescopes in total can actually work together to create an image. It's called an interferometer. And basically each of them is producing an image. So you can look out there. This is a simulation, obviously. So that's the Pacific Ocean in the background there. So those are the auxiliary telescopes. So there's 4 large ones, 4 unit telescopes. There are 4 auxiliaries. And they work together. I think coming up soon it shows you that each of the unit telescopes has an 8-meter mirror. It's about 28 feet. There's 4 of those. The auxiliaries have about a 6 feet mirror, just under 2 meters. But when they work together, the 4 units give a mirror that size, about 100 meters in diameter. And when you add in the 4 auxiliaries, you get 150 meters. That's the equivalent mirror size that's working. So each of those mirrors pumps out information. You can see it all going in. It goes into that central building, which is sunk down below the platform, and that's where it gets processed. So basically, on an interferometer, let's talk about that. This is an elevation of one of the mirrors, one of the big ones. So it's the mirror itself is in the section about here. There. It weighs 22 tons on its own. It's made out of ceramic glass material. Has pretty much a zero thermal coefficient of expansion. It's not totally rigid, which is a bit of a problem because the telescope has to keep moving. But there are actuators all around the rim of that mirror to compensate for that. So when the telescope tilts, the mirror is going to distort a little bit, and actuators come in and correct for that. The reflective coating is aluminum. It is about 20 grams of aluminum on the entire mirror. That's about the weight of an empty pop can. It's put on by, I think, magnetron sputtering. So basically they create a plasma of aluminum and spray it onto the mirror. And it creates this wonderful polished effect. Mirrors are cleaned monthly by hosing. You'll see an example of that later. The whole mirror gets recoated every 2 years, and the total weight of the structure that holds the mirror and the thing is about 380 tons. It's entirely silent when it rotates. You cannot hear it. And in fact, you can actually, the guy told me, you can do that. You can put one on the boundary, the rotating turntable. You can put 1 foot one side of it, one the other, and just push, and you can get that telescope to rotate. So I was trying it, and then he said, "Don't be silly, we put the brakes on." But yeah, it's beautiful. It floats on a film of oil. It's, I'm sure it's only a few molecules thick, the oil, but everything has been ground so flat, so perfect, that it's just amazingly, the technology is just always so impressive. So what does the VLT do? This is it's been one of the most productive research telescopes ever. Gets used a lot by scientists. So this is just one thing that I found quite interesting. It's been tracking orbits of stars that are close to the black hole at the center of our Milky Way. So there's quite a few of them. They're just essentially, those stars are whizzing around the black hole. Shortest orbital period of one of those stars, 12 years. Goes all the way around. That is incredible speed. So anyway, so I mentioned it's an interferometer. So what is interferometry? Well, essentially, it's the combining of images from separated telescopes into one image. It can increase the resolving power of a telescope a lot, because the greater the separation distance, the greater the resolution you're going to get. It's essentially, instead of having one mirror, you have 2 mirrors and then 3 mirrors, and the further away that next mirror is, increases the resolving power. But unfortunately, it's not that easy. So the distance that the light has to travel to each telescope has to be made identical for every telescope to within half a wavelength. So you can see, I'll go to the next slide. So this is, it shows 2 mirrors. You get the same star reflecting to both of them, but it has to go a little bit longer distance to one telescope compared to the other. And that means that there's a delay there, so that they're no longer in the phase together. And so you have to take one of those light things and put it through an optical delay line. And that's what this guy on the right is doing. This is underneath the Paranal, the VLT telescope. It's got optical delay lines for every single telescope that there is there, and he's adjusting them to get all the light in phase. Yeah, so this is just saying that why do an array is because we can't really build telescopes that big. But the array is in a way, it's a cheap way of doing it, but it does seem to work. So another telescope also doing distant objects is the ALMA, the large millimeter, submillimeter array. The large refers to the array, not the large millimeter. So it operates in a different part of the EM spectrum. It's around 1 millimeter wavelength, actually from between 3 millimeters down to 0.3 millimeters. It observes in 10 bands in that space. So going back to the diagram. Yeah, you can't really. Contrast is not very good there, but basically around 1 millimeter there's a dip in the opacity of the atmosphere, and that's what this array of radio telescopes is trying to pick up. Normally you'd still lose a lot of transmission at that wavelength, but the Atacama is high up, it's very dry, and the two things that really interfere with the predictors are oxygen molecules and water vapor, and some like CO2 to some extent as well. So I can tell you now that the array is up at 15,700 feet, and there's a distinct lack of oxygen up there. We never got up there, unfortunately. We wanted to go, but anyway, the wavelength of light, visible light, is about 1/1,000,000th of a meter, 1 micron. That's in the infrared area. Radio light has a wavelength 1,000 times longer. So if you want to capture images as sharp as those on optical telescopes, you need a radio telescope that is 1,000 times larger than the optical one. And that's because, and I'm putting in this equation because Mike encourages equations, the diffraction limit of scopes is basically proportional to the wavelength divided by the diameter of a mirror in this case, or a lens, or in the separation distance between two receiving radio dishes. So that's the limit, and you need a distance of separation 1,000 times bigger than you would get on an optical one. So if you have a mirror of about 8 meters diameter, say, then you need to go 8,000 meters to separate two radio dishes to get the same resolution. So that means you need a big area to do this. An interferometer combines light in pairs. So there's two telescopes, and that's all it can do is just take two signals coming in and adjust for them. So each pair of observations has to be synchronized. So how many pairs in an array? Well, here's another equation. So it's n factorial divided by 2 times n factorial minus 2. So at VLT in parallel, n equals 4 or 8 typically, depending on how many telescopes they're using. So the number of unique pairs is 6 or 28. So those are 28 pairs at most that have to be adjusted on the delay lines. So judging by the guy who was laboring over that, that's probably quite a lot of work. I think they do most of their observations in just four telescopes, 6 pairs of observations. ALMA, the large array of dishes, has 66 satellite dishes receiving signals. So the number of unique pairs in that is 2,145. I don't think anybody could do delay lines like that. So what they do, they reduce the frequency. I think it's through heterodyne oscillations to basically makes the signal a little simpler to work with, and then they put it through a correlator. And this is the photo of the machine that runs all the time underneath the array. It's never turned off. It is continuously working because the Earth is always rotating, so those distances are forever changing. When COVID took place, they wanted to close ALMA down, and they were saying, "No, you can't do that. No, no, no. We have an atomic clock going. We need the atomic clock to keep working because we use it to synchronize our historical data with the data that we're going to be using later. And if they turned off the clock, it would lose all that data. It would be useless. So they kept the clock going. That was the only thing that was working in ALMA for 2 years. So in ALMA, this is an aerial view of the satellite dishes up at 15,700 feet. The large dishes each have a diameter of 12 meters. The smaller ones, 7 meters, they're right in the middle. And you can see, yeah, that's the compact array. They use that for fine focusing of the other dishes. So I counted them all up here. There's about 30 in sight. So there's another 26 somewhere spread around. I think there's one in the distance on the right, and then the other ones will be spread around. It takes it's a 16-kilometer area where they can put the dishes, and there's lots of spots around where they can plug in a dish over here or over there, depending on what they need. So when we were there, we were not able to go up to the array, which is probably not too bad a thing. The reason we couldn't go was because of insurance. And the insurance requires that everybody who goes up there has a personal supplemental oxygen bottle just in case. And they didn't have enough to go around. So there were 18 of us, and we didn't go. But we did have a good look at one of the units that was down for maintenance. So each of these dishes weighs 100 tons. It's carried down there on this huge transporter mechanism, which drives along. It goes under and it picks up there's 2 lugs on the side of the thing there, and one on the other side as well. So the transporter drives underneath it, and then you can see on the transporter there's like a ramp there. So basically it drives in until it catches it, then it lifts it up, and then drives back. It's a 6-hour drive. It could only be moving at about sort of 7 or 8 miles an hour, I think. Where it's a huge thing, 100 tons each time. And these are some of the things that the ALMA have been able to put together. So these images are basically interferometric images. So I'm not sure how they managed to get from interference patterns to building up a proper image. I gather it has things to do with Fourier synthesis and contour mapping. That's all I know. And it sounds very complicated, and I'm sure it is. But what they have here is pictures of, on the left one, is a solar system in the making. So that's a pile of dust surrounding a sun. The sun is in the yellow bit in the middle. And you can see the tracks around it, circular tracks. And that's planets going around, sucking up the dust that's there, growing in size, and becoming eventually a rocky planet like the Earth or Venus or Mars, or more likely seems to be building up gases, and you get a gas planet such as Jupiter or Saturn or Neptune. The one on the right shows a planet sucking in dust. So it's a growing planet. It's quite a big planet. It'll be a gaseous planet like Jupiter, but be bigger than Jupiter probably. And it's revolving around, sucking in gas to grow bigger. And that got a lot of interest when they saw that one, because it's such a visual hit. Anyway, so basically this was the control room for Atacama. Hardly used nowadays. In COVID, they remotely made it a remote operation from Santiago, and people went to Santiago to run the machine, and then they decided they didn't really want to go back to the operations. The operations headquarters is at 12,000 feet. It is in the middle of nowhere. We were in San Pedro de Atacama, a tiny place, and it took us 3 hours to get from San Pedro to this place, and San Pedro is an hour and a half away from Calamar, which is a mining town, and that's a 2-hour flight away from Santiago. So for some reason, people didn't really want to go back to here. So we had a tour of the whole thing, the labs and everything they have there. It was almost deserted. Strange. So anyway, we're in Chile. All this, we do a lot of driving around, I'll tell you. And you see things on the way that are interesting. So this was a road sign, watching out for, was it llamas? But later on we actually saw, but it's not a llama, it's a vicuña, which is a small version of a llama. And there were many, many vicuña. We saw a rhea, which is like a flightless bird. And there was a flock of them, which unfortunately the van was driving too quickly and wouldn't stop for us. So we just got that one picture. And then just on the right is the desert in bloom, El Desierto Florido. So this was just giving the lie to the fact that this is the driest desert in the whole world. Last winter, it rained. They had the whole half an inch of rain over the whole winter. And this is what happened just 4 weeks ago, I think. The flowers bloom. It only lasts 2 weeks, and then they die, and then it's probably going to be 7 years before it happens again. But people flew from all over the world to go and see that. I was tempted. And finally, we're going to talk about a survey telescope. So this is Vera C. Rubin. Is a woman. It was actually called the Legacy Synoptic Survey Telescope. Bit of a mouthful, and they renamed it in honor of Vera C. Rubin, who was an astronomer. Did a lot of work in the 60s, and she was never recognized for everything that she did. Not at the time, anyway. What she did essentially was discover dark matter. She was studying the rotation of galaxies and noticed that, these galaxies are rotating very, very quickly. They should be flying apart if you just use normal gravitic sort of formulae. the stars should be flying off left, right, and center as they're rotating, but they weren't. They were stable. So she said, "There's got to be something else there, but I can't see it." And she put out her findings. They were verified. She got some recognition there, and eventually now, of course, we realized dark matter. It's nobody really knows what it is anyway, but it's obviously something to do with undiscovered heavy particles down at the sort of nuclear atomic level. Anyway, nobody's really sure. It is. Anyway, she has a thing now. This telescope, one of its main purposes is to look for where dark matter is by observing changes. And so she got some recognition in the end. It's very good. So, survey telescopes, the features are wide field of view, extremely high resolution, and speed. Like they have to take photos of the Earth, of the sky, one after the other. So this is going to show a little clip here, which is an image of a simulation of what the telescope will do. Oh, it's not coming up.
Are you trying to play your video? Yeah, so you gotta go back to your
Okay.
presentation. Mm-hmm. Let's go to presentation. So we're gonna get out a presentation view. Now, is this the video?
Yeah, that's it. Okay, so this little dot here, this is the real time is in subtitles below it, so it's actually an accelerated thing. But that is the telescope taking pictures. Basically, it's the entire Orion constellation that it's taking a picture of, and it just goes and goes and goes, and it can do an entire constellation in 21 minutes. And I'll show you an example of the detail of the photos later on.
Just gotta get out your video. Back to presentation. From current
Okay.
slide? Just this button there?
The current slide is down here.
Oh, yeah, you're near the end, maybe.
There we go.
And for the current slide. If you tap
Okay.
that button there.
Yeah, from
slide.
current slide, yeah. So this is the photo on the left, is when I was there. And we were talking to the lady, sort of looking very laid back in her control chair. She's in charge of the control room. Those people in the back, and there were about an equivalent number behind me as well. They're furiously working on running software routines because they're planning to get this telescope operational in 1 week's time. And they were busy. I'll tell you, they were busy. It didn't take 1 week, it took two and a half, I think. But eventually they got a thing, and then the Vera C. Rubin telescope had what they call first light. It's when the telescope gets actually operational. And so they turned it on, and it didn't blow up or anything, so they called everybody into the control room and they displayed what they found. And we'll see a little bit of that later. But you can see they're pretty happy with the results. Probably these guys have been working on this for like 6 months, 12 months, getting everything ready, and everything worked. Amazing. So the telescope itself, what is it? Well, it's a very unusual design for a telescope compared to the distant object ones. So it's a triple mirror instead of a double mirror. But the two of the mirrors are actually made from the same slab. It's a honeycomb of glass hexagonal tubes coated in glass itself and then silvered. But you can see there's like two different foci for the outside mirror and the internal one where the guy is standing. At the top is a convex mirror. And you can see that they trace the light rays from the left, say, going down, and then back up on from the outside of the mirror, up to the convex mirror, down to the interior mirror, and then back up. And what it does, it goes through some lenses, and those are on the front of the camera. So this is the biggest camera in the world, the most detailed. It's 3,200 megapixels. It's about the size of a small SUV. It weighs 3 tons. And that's mounted in the front of the telescope. So you see the telescope is actually quite compact. It's compact because it has to move quickly. In fact, it has to move, moves 10 degrees every second. And it can move, start moving, stop, take a picture. Start moving, stop, take a picture. That's the idea. Every 36 seconds, it takes a picture. So it's quite an amazing design. This is an exploded view of the telescope. And on the right, you can see the telescope mounted in the front of the before the mirrors. The mirrors are down at the bottom there. You can sort of see reflections there. If I'm going to do another YouTube now, so if I get out of presentation mode.
You got it. Down one.
Oh, next one.
That's right. Down a slide.
I've got too many things here. There we go.
And control click.
Yep.
There you go.
8 years to build that. It was all designed by Slack Labs, which is a Stanford linear accelerator in California. They did all the software for the telescope as well. It seems to work perfectly. It's been on the books to build since 2010. That was the first idea floated, and money assigned to it, mainly the National Science Foundation in America. And I just hope, given the current administration, that they keep funding it. So while we were there, while the people were doing the software thing, people were on the telescope polishing it up. Dust is a problem. It's very dry. So they're washing the mirrors. No need for newspapers there. It's not water. It's powdered dry ice. And they spray it on. Of course, it evaporates almost immediately and carries away all the dust that was on it. Because dust is a problem. So the Vera C. Rubin telescope is currently taking pictures, and it will continue to take pictures for 10 years. That's its mission, and while it's doing that, the Slack Labs and so on will be working to give access to anybody to the work that they're doing. It's completely open. And one of the things that they're working on, and this is Mike will be interested in this one, is orbit viewer. So they're going to put in all of the stuff that they see moving, they're going to add it to what's known already, and end up with orbit viewer. So this is a demo that they put out. So the white things are mainly, that's the asteroid belt. The pink things are what they call Trojans, which are things that precede Jupiter. And then there's all sorts of other stuff that they keep adding in. You need a pretty fast connection to the internet to be able to use this at maximum resolution. This is at minimal resolution here, but it's stuff you can play around with. Now, Mike talked about the dwarf planet as a way of enticing people to come along. And then, if there is such a thing, which I don't believe myself, but Vera C. Rubin will find it. And eventually it'll appear on this, and then Mike can fiddle around with it as long as he wants. Anyway, Vera Rubin is a marvelous thing. It's just, it blew my mind away when I was there. It's, I got a really good feeling. You know, sometimes you get good vibes about places, and the feeling of the people who were working there, it was like just everything for science type of thing. It was really a good vibe. So that's essentially it, except for one more thing, which I will leave you with. But thank you for listening. I gather we've been having sound problems all the way through. No change there, eh, Naomi? So I'm just going to put on this last bit. So when you saw the people in the control room going, wow, They were looking at this. Okay, how do I do it?
Yep.
There we go.
Pause a second.
I have to come out of presentation mode.
Yep.
So.
That's okay. We're on it.
So the star-like things you're seeing are stars in our Milky Way. All that stuff in the background are galaxies. It's galaxies everywhere. And probably every galaxy has somebody like me talking about discoveries that can be made. Okay, so. Well, I hope you enjoyed that. Here's Mike.
Okay, so
You'll find your dwarf planet soon enough.
well, we'll see. I think we had agreed beforehand that he would take a break now and then he will answer questions after the break. This was our agreement,
Yes.
was it not? Yeah. So 10 minutes.
I'll be hanging around.
The floor is open to questions. Otherwise, we'll let you go back and continue your conversations.
Okay, you said that the only stars we can see are the ones in the Milky Way galaxy. Is the North Star in the Milky Way galaxy?
Yeah, yeah. Yeah, this is the only ones you can see with the naked eye. You can actually see with the naked eye another galaxy. That's the Andromeda galaxy. It's a very, very faint. Is this plugged in?
Yep.
Yeah. Okay.
Just
Yeah.
hold it closer to your mouth.
Yeah, it's very, very faint, but you can see the Andromeda galaxy. It's the one that is hurtling towards us at about, I don't know, 3 million kilometers per hour. And it will actually merge with the Milky Way in 1 billion years or something. Anyway, it will get here eventually, but I think it's far enough away that we don't need to worry about it. Civilization might only last a few more years anyway.
Yeah, you're talking about a 12-year period for some of the stars that are revolving around the black holes. So they must be going pretty close to the speed of light. Or what's the diameter of their orbit?
I don't know the answer to that, but are they going close to the speed of light? I would think yes. They're very, very fast. They're orbiting. I don't know what the diameter of the orbit is. It's probably still quite a few light years, but even so, it is very, very fast. And I know that reading the synopsis of the paper, it showed that they were measuring the planets, I think, on a weekly basis, and seeing, even from our distance, they were seeing displacement. So they've got to be moving fast for that to show up. Yep.
I was wondering why they had to put the radio telescopes in that area as well. I mean, I can understand why you'd want the dry conditions for optical telescopes. But is there some reason for setting in a radio telescope array on the same conditions?
Which radio telescope?
The radio telescope array that you...
Oh, it's up on the what they call the Chajnantor plateau. I'm not quite sure what you're getting at, to be honest.
Why did they put the radio telescopes there? Because they're not sensitive to the same reasons that the optical telescopes are sensitive
Oh,
to.
no, that's right. The radio telescopes have to go up high because the atmosphere is still partly opaque to them. For optical, obviously, you're back in the visible wavelength area and the skies are clear. Well, not tonight, but yeah, it's just a narrow window around about 1 millimeter wavelength, and still the atmosphere is partly opaque at that point. But the main reasons that it's opaque is because of oxygen molecules and water vapor, and at 15,700 feet above sea level, on the western side of the Andes, it is dry, it is warm, relatively warm, and obviously at that elevation, not a lot of oxygen either. So they can get by. It's not perfect, but it's close enough to receive a decent signal and to do analysis.
How long does it take somebody to acclimatise to working at that altitude before they
15,000?
regular efficiency?
At 15,700 feet, not everybody is going to be able to work in that area. So that's why everybody who goes there as an employee has supplemental oxygen, and they're encouraged to use it all the time. So it comes in a little bottle. I think some people who have breathing problems, asthma and so on, can also get these things here, even here, down at sea level. But for insurance purposes, they are required to have it and to use it, even if they don't feel like they need it. They're supposed to keep doing it, like they give a schedule. Once every 15 minutes, take a couple of breaths of oxygen, and just to keep your mind clear, because your mind fogs up when you start depriving people of oxygen. Your mind fogs up. Apparently, you don't notice that, so you can have a serious accident if you're working in an area, that has a bit of hazardous conditions to it. If you're working up high, for instance, or working with the machinery. So the insurance people tell people that they have to use the oxygen while they're up there, but they don't do a lot of work. The main thing that happens up there is the big transporter drives up there, picks up an antenna and drives back down again to the sort of maintenance sheds, which are about 12,000 feet, and that's where they work on them. So I was up there at about a couple of days. We went up to 14,500 feet, and I was okay. I was just strolling around, not doing anything strenuous. One time it was flat. We were at the Giza field up at 14,500 feet, and that was interesting. And the other time we went to look at the salt lakes that are way up high in the Mount Andes, and that was on the side of a hill. So I was fine going from the van down to the viewing area, and then I had to climb back up the hill. And you can really feel it after just, 12, 20 paces, you start sort of slowing down because you're breathing, sucking in air as much as you can, but you feel it going. Any sort of exertion, you would feel it. So
you can feel it at 7,000 feet for that. You feel it at Los Alamos, for example, if you're up there, you've just arrived there, and you run up a set of stairs, you start breathing very hard.
Yes, I can believe that.
That's 7,000 feet.
Yeah. Everywhere we stayed was all on one level, so no stairs. But I didn't have any problems. And the first day that we arrived, we flew from Santiago to Antofagasta on the coast. Stayed in a hotel right by the coast for the one night. And then the next day we went up to 8,000 feet to the very large telescope. And we were walking around there. And again, I didn't feel anything problem. Oh, I did have sinus problems for that first day, which I attributed to much lower air pressure. Maybe it wasn't that, I don't know. But that was the only ill feeling I had. Yep.
Tom?
How did you arrange for your tour to go visit all these facilities? Because they must be high security and hard to get into.
Yep. So the most accessible of the 3 places we went to is the Very Large Telescope. They have tours every Saturday. You have to book them. They take about 20 people maximum at a time, and I think they have 4 tours on Saturday, so that's 80 people can get in. You're required to go through a safety briefing before they let you in. They have all sorts of safety advice, like obviously, like when you're leaning over railings, don't drop things. It's some pretty obvious stuff, but you have to go through it. I'm sure the insurance requires that as well. So but you have to book ahead of time. The guy who was organising it, Rodrigo, said he books 3 months in advance. So you have to know when you're going to be there, arrange to be there. Alma, the place with the radio dishes way up high, it's difficult to get in there. Rodrigo, our guide, knew somebody personally who happened to be the director of outreach at Alma, and so that was pretty smooth going in there. Vera Rubin, you can't get in unless you know somebody. And so Rodrigo managed to get that in as well. I was surprised because they were so busy when we got there getting ready for first light. I'm surprised they let us in, to be honest. But they were really, as I said, I got a really good vibe there. They were all excited about what was coming up and wanted to get it done. They were wanting to tell people about it. Very nice vibe there. It'd be a good place to go work.
You forgot to mention that this is an organized tour by New Scientist. And if you look at the magazine, which is in the library, you'll see a lot of tours like this being advertised.
Coming back to dark matter, I want to ask a very elementary question because I don't really understand where we're coming from at all. So presumably there's a gravitational field from the atoms and nuclei that are in there. Would those also have a slowing down effect through friction? Because whatever's whizzing round and round is going to be slowed down by that atmosphere that you can't see. I don't understand the 2 points taken together.
That's about the same amount that I understand.
I can answer a little bit.
Oh, Mike has all the answers here.
Not all the answers, but the point is that all the atoms, the gravitational effect of all the atoms that they can see, if you calculate what the orbit of all these stars going around the central point is, and it just doesn't add up. There's not enough gravitational effect from any of the atoms you can see to explain that, and so you theorize that there's this stuff called dark matter which does not interact electromagnetically or any other way, so its presence is only felt gravitationally. And then the question becomes, where is it and what is it? And that is a big question mark. Is that... I read a lot about that, so...
Okay, now that's a fair answer. So it doesn't interact mechanically either.
Sorry?
it, it, it,
It does not interact it does not interact with the electromagnetic, electrically, magnetically, any other way that we know of. It just interacts gravitationally, which is why they're having so much trouble finding it.
doesn't interact mechanically either.
No.
No,
No.
because that would be electromagnetically.
I think the current thinking is that there is some fundamental particle involved here that we can't locate, but it carries a force, such as a gravitational force. It's not a graviton because it doesn't obey the theory behind gravitons either. But it's got to be something fundamental that we don't understand. Haven't found it yet. It'd be fascinating when we actually do come up with an explanation for it.
I can add one more thing. In addition to watching, like I was very skeptical of all this when I first read about it, because I'm thinking basically the way you're thinking. But there's some more evidence for the dark matter. If you look at a star far away or some source of light, you can see that it has been bent by something that you can't see. This is the Einstein bending of light or by matter. And there's something there that is not, you can't see it, but it has bent light. And they can actually map out where all this dark matter is just by looking at the gravitational lensing of stars way off in the background, which is another bit of evidence that there is something there, but what it is, well, there's a lot of people spending a lot of work trying to figure that one out.
And this is one of the missions of the Vera Rubin telescope, is with all of its cataloging that it's going to be doing, they're going to be able to look for these sort of effects quite in detail and hopefully come up with some explanations before I die. Unlikely.
I have a question.
Yeah.
That picture you showed right at the very end,
Yes.
was that a time lapse of everything that it's seen over a period of time, or was that an instantaneous picture that it took and then we're just panning around one image?
Yeah. So you have that final image, which they call it the cosmic treasure chest, which I think is a very poetic name for it. It is one image. In fact, it is just a small fraction of the one image that they took for first light. I think they said that if you take the entire image and showed it in full resolution on TV screens, it would take 40 high-resolution TV screens to show the one image. And so all we're seeing there is just a little corner of it. And as you can see, like it was outside of the stars, which are close to us. Behind it was galaxies. It just seemed to be galaxies going away as far as you can see.
And that's all in one image?
One image.
Wow.
So keep tuned, Vera Rubin. The orbit viewer is available on the Vera Rubin site. It's not really an app, but you can watch it on the internet at various resolutions. So if you've got a very fast resolution and a very fast computer, the stuff that they have on there is, it just blows your mind. And they're adding to this well, not every day, not yet, but eventually, when it gets fully operational, they'll be adding stuff every day. Anyway, any more questions?
What's the nature of the spiral that the galaxy forms? What's the nature of the spiral?
Well, in ours it is a spiral, which I showed you. So it's the galaxy rotates once every 250 million years. And basically, because of the gravitational rotation, that's what causes the spiral arms. and but that's only one form. The galaxies can take other forms. There are galaxies that are just clusters, basically, steady clusters. There's elliptical galaxies, quite common. What else, Mike? No, okay. Those are the three types that you can see regularly.
Thank you.
Okay.
Well, if there's no more questions, I would like to thank our speaker for a very interesting talk, and I welcome you all to the next talk in about a month. Thank you very much. And don't forget the exit fee.